Welcome to today's lecture on Chapter 21. This is talking about the cardiovascular system, specifically blood vessels and hemodynamics. Starting off by looking at the structure and the function of the various types of blood vessels. There are five main types of blood vessels that are going to be found in the body. These are going to be the arteries, the arterioles, the capillaries, the venules, and the veins. Arteries are going to carry blood away from the heart to other organs, and these are going to be large, elastic vessels. They're going to be, this is where large elastic arteries are going to leave the heart and are then going to divide into medium-sized muscular arteries that can branch out into the various regions of the body. At that point then, these medium-sized arteries are then going to divide further into smaller arteries, which are in turn going to divide into even smaller arteries, which are called arterioles. As these arterioles enter a tissue, they're going to branch into many little tiny vessels, and these are called blood capillaries, or just plain old capillaries. So the thin walls of these capillaries is going to be excellent for allowing the exchange of various substances like blood and oxygen and nutrients between the blood and the body tissue. Groups of capillaries within a tissue are going to then unite to form small little veins called venules, and in turn these little venules are going to merge to form progressively larger vessels called veins. And veins are the blood vessels that are responsible for conveying blood from the tissue back to the heart. So looking at the various structural components of our blood vessels. In general, a blood vessel is going to have three layers. We have the Tunica Interna, also known as the Tunica Intima. This is the innermost layer of the blood vessel. You can see this here, our inner layer. And this is going to be the layer that's adjacent to the lumen of the vessel, or the hollow part of the vessel. The Tunica Media is the middle layer of our vessel. Here we can see this layer. I'm showing you in the artery because it's much larger in the artery. It's easier to see, so we can see that. This Tunica Media is, like I said, our middle layer, and it's going to be made up of smooth muscle as well as elastic fibers. And then our outermost layer is going to be the Tunica Externa, and this is the layer that's going to be adjacent to most of that surrounding kind of tissue. So starting off looking at the Tunica Interna. So although this layer is going to be made up of multiple parts, we've got our endothelium, our basement membrane, and then our internal elastic lamina. So it's made up of these three layers, but this tissue is going to contribute fairly minimally, or this layer is going to contribute fairly minimally to the thickness of the overall thickness of the vessel wall. The tunica interna is going to be closest to the lumen of the vessel, and therefore is going to have direct contact with the blood, and is going to also be continuous with the endocardium of the heart. So the epithelium of this layer of the vessel is going to be a thin layer of flattened cells that are going to lie in the inner surface of the entire cardiovascular system. This is the heart and all of the blood vessels. The endothelial cells are going to be active participants in a wide variety of vessel-related things. This is going to include the physical influences on blood flow, the secretion of locally acting chemical mediators that are going to influence the contractile state of the vessel's overlying smooth muscle, as well as the assistance with capillary permeability. So in addition to this, their smooth luminal surface is also going to help to facilitate efficient blood flow by helping to reduce the friction of the blood vessel against the actual components of the blood. So it's nice and smooth in there. The second component of the tunica interna is going to be the basement membrane. Right, so we've just discussed our endothelium. Next is our basement membrane. This is going to be superior to the endothelium. So it's our next layer up. This is going to provide physical support, a physical support base for the endothelial layer, and it's also going to be used as a framework of collagen fibers. It's going to allow the basement membrane to provide a significant amount of tensile strength, and this is going to also be allow it to maintain its properties to provide resilience for stretching and recoiling. So it's going to allow it to maintain all of those properties. The basement membrane is going to anchor the endothelium to the underlying connective tissue, while it also regulating the molecular movement. The outermost part of the tunica interna forms the boundary between the tunica interna and the tunica media, is then our internal elastic lamina, which you can see here. It looks kind of like Swiss cheese. So this internal elastic lamina is going to be a thin sheet of elastic fibers with a variable number of window-like openings that are going to give it the look of Swiss cheese, like I said. You can see that. It really does look like Swiss cheese. These openings are going to help to facilitate diffusion of materials through the tunica interna to those thicker tunica media layer that we see here. The next layer we have is the tunica media. All right, this is a muscular and connective tissue layer that's going to display the greatest variability or variations among the different types of vessels. So this is the layer that's going to be the most different between all the different types of vessels that we'll discuss. So in most vessels, this layer is going to be relatively thick, and it's going to be made up primarily of smooth muscle cells, as well as a substantial amount of elastic fibers. Separating the tunica media from the tunica externa is a network of elastic fibers, which are called the external elastic lamina, and this is going to be part of the tunica media. The primary role of these smooth muscle cells is going to be to extend circularly around the lumen like a ring that's going to encircle your finger, and this is going to be what's responsible ultimately for regulating the diameter of the lumen of these vessels. So in increasing any kind of increase in the sympathetic stimulation of the nervous system is typically going to stimulate the smooth muscles to contract, and this is going to cause them to squeeze on the vessel walls, and this is going to result in a narrowing of the lumen. This is going to cause a decrease in the diameter of that lumen, like we said, and this is called vasoconstriction when we have this decrease in our diameter of the lumen of our vessels. So in contrast, when our sympathetic stimulation decreases, or in the presence of various chemicals, things like nitric oxide or hydrogen ions or lactic acid, or sometimes in response to blood pressure, this is going to cause smooth muscles fibers to relax. And this resulting increase in lumen diameter is called vasodilation. So we're dilating the blood vessel, essentially. So in addition to regulating blood flow and blood pressure, smooth muscle is going to contract when a small artery or arteriole is damaged. This is going to be something called vascular spasm, and this is going to help to limit the loss of blood through that injured vessel. So it's going to help to kind of seal that off a little bit. Our last layer of blood vessels is going to be called the Tunica Externa. This is the outermost layer of our blood vessel. You can see that here. It's a nice big section of an artery. This dark outer layer is our Tunica Externa. This is going to be made up of elastic and collagen fibers. The Tunica Externa is going to contain numerous nerves, and especially in those larger vessels, they're also going to tiny blood vessels are also then going to supply the tissue of the vessel wall. So this is more common in the really big vessels. So these small vessels are that supply blood, that are going to supply blood to the tissue of the vessel are called vasa-vasiform, are called the vasa-vasiform, also called the vessel to the vessels in English. So these are so big for some of these vessels that they need their own blood supply, essentially. It's pretty cool. These vasa-vasiforms are going to be fairly easily seen on large vessels, such as the aorta. In addition to the important role of supplying the vessel wall with nerves and self-vessels, the tunica externa is also going to help to anchor the vessels to that surrounding tissue. So now that we've looked at the various layers of each of these, just generally of these of the blood vessels, let's look at the actual individual vessels, or the different types of blood vessels that we have. For starters, we have the arteries. So the wall of an artery, like we said, is going to have those 3 layers of a typical blood vessel. But it's going to have a thicker muscular to elastic tunica media. So due to their plentiful elastic fibers, arteries are normally going to have a very high level of compliance. And this basically just means that their walls are able to stretch easily or expand without tearing in response to small increases in pressure. Arteries are able to carry blood away from the heart to the various tissues in the body. And the walls of the arteries are going to be very elastic, which allows them to absorb the pressure that's created by the ventricles of the heart as they pump that blood into the arteries. So because of the smooth muscle in the tunica media, the arteries are going to be able to regulate their diameter. We have several different types of arteries that we can discuss. We've got our elastic arteries. These are also called conducting arteries. These are going to be larger in diameter. They're also going to have more elastic fibers and less smooth muscle. And functionally, they're going to work as a pressure reservoir, which we'll talk about in a little bit. The other type of artery that we have is the muscular artery. These are also called distributing arteries, and they are going to have a medium-sized diameter. They're going to have more smooth muscle, less elastic fiber, and they're going to contribute. They're going to be involved in distribution of blood to the various parts of the body. So starting off with our elastic arteries, looking at these elastic arteries are going to have the largest diameter among any of our arteries, but the vessel walls are going to be comparatively thin compared to the overall size of the actual vessel itself. So these vessels are going to be characterized by a well-defined internal and external elastic lumina, and they're also going to have a thick tunica media. This is going to be dominated then by elastic fibers, and this is called elastic lamella. The elastic arteries are going to include the 2 major trunks that are exiting the heart, the aorta and that pulmonary trunk that we've discussed. And then along with that, we're also going to have the aorta's major initial branches. These are all going to be elastic arteries. And because they conduct blood away from the heart to the medium-sized and more muscular arteries, these elastic arteries are also going to be called conducting arteries. These elastic arteries are also going to be involved in performing an important function, and this is going to be to help to propel blood onward while the ventricles are relaxing. So as blood is ejected from the heart into these elastic arteries, their walls are going to stretch, and this is going to easily accommodate that surge of blood that's coming from the ventricles. So as they stretch, those elastic fibers are momentarily going to store that mechanical energy in their walls, and this is going to function as a pressure reservoir. So we're essentially storing up that pressure to be used later. So when the elastic fibers recoil, they're going to convert that stored potential energy in the vessel into kinetic energy of the blood. And this is then going to continue to move the blood through those arteries, even while the ventricles are relaxed. So it's kind of helping to shoot it out through of those arteries. Next, we have the muscular arteries. These are going to be medium-sized arteries that are called muscular arteries because they're going to have a tunica media that's going to contain more smooth muscle and fewer elastic fibers than what we would see in the elastic arteries. So a large amount of smooth muscle, about 3/4 of the total mass, is going to make up the wall of the muscular arteries, and it's going to be relatively thick. So therefore, our muscular arteries are going to be capable of greater levels of vasodilation and vasoconstriction, which is going to allow for greater adjustments to the rate of blood flow. The muscular arteries are going to have well-defined internal elastic lamina, but however, they are going to have very thin external elastic lamina. So these 2 elastic laminae are going to form the inner and outer boundaries of our muscular tunica media. So because the muscular arteries are going to continue to branch and are ultimately going to distribute blood to each of the various organs, these are called distributing arteries. So the Tunica Externa is often going to be thicker than the Tunica Media that's found in the muscular arteries. So this outer layer is going to contain fibroblasts, collagen fibers, as well as elastic fibers that are all oriented longitudinally. So the loose structure of this layer is what's going to ultimately permit these changes in diameter of these vessels, allowing this to take place. However, it's also going to prevent a shortening or a retraction of the vessel if it's cut, which is a good thing. If you were to accidentally nick this vessel, you'd hate to have to go digging up in there to retrieve it. So because of this reduced amount of elastic tissue that's found in the walls of these muscular arteries, these vessels do not have the ability to recoil and to help to propel the blood like we would see in the elastic arteries. Instead, this thick muscular tunica media is going to be primarily responsible for the functions of the muscular arteries. So the ability of the muscle to contract and maintain a state of partial contraction is what we refer to as vascular tone. And this is what was essentially going to stiffen the vessel wall. And it's going to be really important for maintaining vessel pressure as well as efficient blood flow. So moving on, let's look at something called an anastomosis. This is going to be the union of the branches of two or more arteries that are going to supply the same region of the body. This is going to provide an alternate route for blood flow, and if blood flow is going to stop for a short time to a part of the body when normal movement is compressed for some reason, or if a vessel is blocked by disease or injury or by surgery, then circulation to a part of the body, or to that part of the body, is not necessarily going to be stopped overall. So the alternative routes of blood flow to the various body parts through an anastomosis is known as collateral circulation. So arteries that do not have an anastomosis are called end arteries. And if these are blocked, then blood cannot get to that particular region of the body, and necrosis can start to occur, which is a very bad thing. So if you remember from A&P 1, necrosis is just a pathological cell death. So that's really something you want to avoid. So moving on then, let's look at the arterioles. Right? These are going to be very small, almost microscopic arteries that are going to be responsible for regulating the flow of blood to the capillaries. So through vasoconstriction and vasodilation, arterioles are going to assume an important role in regulating blood flow from the various arteries into the capillaries and in altering the various arterial blood pressure. So the terminal end of the arterioles is called this region is called the meta-arteriole, and it's going to taper towards the capillary junction. So at the meta-arteriole capillary junction, where those two meet up, the distalmost muscle cells are going to form a precapillary sphincter. These are going to monitor the blood flow into the capillaries, and the various other muscles or muscle cells in the arterioles are going to also regulate the resistance to blood flow. So next we then, in like the order of things, we have our capillaries. These are going to be the smallest of the small of our blood vessels, and this is going to form kind of a U-turn that's basically responsible for connecting the arterial outflow to the venous return. So this is where blood is flowing from the arteries back to the veins. This is where we're doing our U-turn here. So the flow of blood through the capillaries is going to be called microcirculation, and capillaries are found in nearly every cell in the are found near almost every cell in the body. But their distribution is going to vary with the metabolic activities that's going to vary based on tissue type. So these capillaries are going to have walls that are thin, and they're going to be composed of only a single layer of cells. This is the epithelium, and then a basement membrane. The primary function of these capillaries is going to permit the exchange of nutrients and waste between the blood and the tissue cells through the interstitial fluids. Capillaries are going to branch to form an extensive capillary bed or a network throughout that tissue. And this network is going to increase the surface area, which is really great in allowing a rapid exchange of large quantities of materials. So the flow of blood through capillaries is going to be regulated by vessels with smooth muscles in their walls, just like we've talked about, and rings of smooth muscle fibers called precapillary sphincters are going to be responsible for regulating blood flow through these capillaries. So these sphincters are going to be, here we can see our precapillary sphincters. These are responsible for regulating the flow of blood here through these capillaries. We have several different kinds of capillaries, 3 to be specific. We have our continuous capillaries, our fenestrated capillaries, and our sinusoid capillaries. A continuous capillary is going to be the most common type of capillary that we experience in the body, and this is going to be where the plasma membranes of our endothelial cells are going to form a continuous tube that is interrupted only by the intercellular clefts, and these are going to simply be gaps between neighboring endothelial cells. Our continuous capillaries are found in the central nervous system, as well as in the lungs, the muscle tissue, and in the skin. Our next type of capillary that we have to discuss is the fenestrated capillaries. This is where the plasma membrane of the endothelial tissue cells is going to have fenestrations. These are basically just little small pores. You can see here are little fenestrations, little holes, pores in the vessel. And these are going to be between 70 and 100 nanometers in diameter. So they're quite small. These fenestrated capillaries are going to be found in the kidneys, the villi of the small intestine, the choroid plexus of the ventricles in the brain, as well as in the ciliary processes of the eyes, and most of those endocrine glands. So this is really going to be a great place where a lot of filtration or exchange is going to occur with this fenestrated capillaries. And then last but not least, we have our sinusoid capillaries. These are going to be wider and are going to have a more winding kind of shape than what we would see in our usual capillaries. Their endothelial cells may have a very large fenestrations that we see here. So these look kind of like Swiss cheese again. So in addition to having an incomplete or absent basement membrane, our sinusoids are going to have a very large intercellular clefts, and this is going to allow for proteins and in some cases even blood cells to pass from a tissue into the bloodstream. So for example, any kind of newly formed blood cells that are going to be able to enter the bloodstream through a sinusoids of our red bone marrow. So these are much larger. They allow for the passage of much larger molecules than what we would see in our fenestrated capillaries. So additionally, these sinusoids are going to contain specialized lining cells that are going to be specifically adapted to the function of the various tissues that they are associated with. So sinusoids in the liver, for example, are going to contain phagocytic cells that are responsible for moving any kind of bacteria or other debris from the blood. And in the spleen and the anterior pituitary, as well as in the parathyroid and adrenal glands, these are also going to be organs or areas that are going to have these sinusoid kind of capillaries. So the next type of vessel that we're going to discuss are the venules. So unlike their thick-walled arterial counterparts, venules and veins are going to have very thin walls that do not readily maintain their shape. So venules are going to drain the capillary blood and are going to begin the return trip of blood back towards the heart. So these venules that initially receive blood from the capillaries are called post-capillary venules. That makes sense. And they are going to function as a significant site of exchange for other types of nutrients and waste, as well as white blood cell immigration. And for this reason, they're going to form part of the microcirculatory exchange unit along with those capillaries. So as the post-capillary venules move away from the capillaries, they are going to acquire one or two layers of circularly arranged smooth muscle cells. These muscular venules are going to have thicker walls across which exchange with the interstitial fluid can no longer occur. So the thin walls of our post-capillary and muscular venules are going to be the most distendable element of our entire vascular system. And this is going to allow them to expand and serve as excellent reservoirs for accumulating large volumes of blood. So, moving forward, then next we have the veins, and these are going to consist of our three main basic layers or tunics, as what we would see in the arteries. But these are again going to have a thinner Tunica Interna, a thinner Tunica Media, and then ultimately a thicker Tunica Externa. These veins are going to have less elastic tissue and smooth muscle, and are therefore going to have thinner walls than what we would see in the arteries. So many veins, especially those that are in the legs, are also going to contain these valves that you can see here. These sort of a folded bit right here, so our valves. And these are going to be thin folds in the tunica interna. And these are going to be responsible for forming these kind of flap-like cusps. And these are going to be really important to help prevent any kind of backflow, keep everything going in the right direction. So like we said, these valve cusps are going to project into the lumen and are going to point towards the heart. So the low blood pressure that we see in veins is going to allow blood that's returning to the heart to slow and sometimes back up. And these valves are going to aid in that venous return by preventing that backflow of blood. This can be unfortunate, though, because if these are ever damaged or anything, that we can have a lot of fluid or blood accumulation, or they can get really big and ugly, and you get those varicose kind of veins. So the vascular or venous sinuses are basically just veins that are going to have thin walls with no smooth muscles. And this is going to prevent them from altering their diameter in any way. So examples of these are going to be the brain's superior sagittal sinus, as well as the coronary sinus that we see in the heart. So the weakening of these valves can ultimately lead to varicose veins. So I've got kind of a neat little video that I stole off of Instagram. You can see their little account here at the bottom. This is looking at how varicose veins actually kind of form. And this is a really interesting little little image video to look at. So we can see those valves working normally, but when they stop functioning normally, circulation is not good, they're not preventing that backflow, and we get this crazy distorted kind of look of these veins that you can see here as our varicose veins. So very interesting stuff. So moving forward then, while veins are going to follow a path that's fairly similar to that of their arterial counterparts, they are going to differ from the arteries in a number of ways, other than their whole structural differences, what we see in the walls. So first of all, veins are going to be more numerous than the arteries that we see in the body for several reasons. Some veins are going to be paired and are going to accompany medium to small-sized muscular arteries. And these double sets of veins that are going to escort the arteries and connect with one another via venous channels are called anastomotic veins. And these anastomotic veins are going to cross the accompanying artery to form kind of like ladder-like rungs between the paired veins. And so the greatest number of paired veins is usually going to occur within the limbs. We also have the subcutaneous layer that's deep to the skin is going to be another great source of veins. So these veins are called superficial veins, and they're going to course through that subcutaneous layer unaccompanied by parallel arteries. So along their course, these superficial veins are going to form small connections with the deep veins that travel between the skeletal muscles. These connections are going to allow for communication between deep and superficial blood flow. The amount of blood flow through these superficial veins is going to vary based on location within the body. And with the upper limbs, the superficial veins are going to be much larger than those that you would see in the deep veins. And they are going to serve as a major pathway from the capillaries of the upper limbs back to the heart. However, in the lower limbs, it's opposite. So the deep veins are going to serve as our principal return pathway. And this is the case so much that the one-way valves in these small anastomosing veins are going to allow blood to pass from these superficial veins to those deep veins, and they're also, however, going to prevent the blood from passing in the reverse direction. So this design is really important because it's going to have really important implications for the development of those varicose veins that we just looked at. So here is just a nice little table of the distinguishing features of the various types of blood vessels in the body. And that is all I have for this lecture today. So as usual, if you have any questions, please feel free to contact me or ask during class. So thanks so much and have a nice day.